Hello and welcome to VHDL lectures. My name is Najim Lawal, and now we shall be discussing basic elements in VHDL. The outline of this discussion will focus on identifiers, classes and objects, data types and attributes, operators, and we shall guide ourselves with some examples. When we talk about identifiers in VHDL, we mean names that we give to the objects and entities and signals that we create. So this kind of names can be used to be descriptive and to tell us more about the architecture, about the entities, about the processes and their associations, perhaps the signals and the variables. There is a little bit of a convention or rules for naming identifiers for giving names to components in VHDL or signals. These names are like, for example, we cannot use reserved words because they are reserved, and because for that reason we need to be familiar with the reserved words in VHDL. Two examples of these are for and if. Another thing is that the VHDL is case insensitive, so you can mix capital letters and small letters at any time when you are creating the signals, the components, and when you are referring to them later in the future. We also have first characters must be a letter and not a number and not a special character, and then the last character cannot be an underscore. Anytime within the names or the identifier, we cannot have two consecutive underscores as a name. We have objects in VHDL, and objects are components that can hold values. That's the way to look at them, as objects have classes and they also have data types. Also have the classes define the kind of operation that can be performed on the objects, and then the type of the object also define the kind of values that the object can hold. We also mean by this that objects can be initialized based on their class and their type. They can be initialized at simulation or for simulation purposes when they are created, but this is only good during the simulation for the engineers to know a default value, and when they are implemented and downloaded on FPGA, they usually take the lowest value, the zero level logic level of the data that is available in the class of the object. So we can define objects within entities, within the architecture, within the processes, and within the package. Signals, classes in VHDL, signals, variables, constants, files, components. These are the kind of classes that you can have in VHDL, and their values can change as a function of time, and then they can be driven and can be read. You can consider them as a connection between one port of an entity to another port or another component, or you can see them as registers that hold values. Variables behave kind of like signals, but they're usually used internally within the process. Of course, you can also have a shared variable defined at the architecture level, but that also means that there might be a little bit of confusion when you are having shared variables. But then one thing about variable is that they are implemented using larger logic resources in the FPGA, so they usually have a very, very not so nice impact on the timing constraints in VHDL of your design. We have constants, which you give the value. It can be a signal, it can be a variable. You give it a value at creation, but then you cannot change the value anytime. So it can be of any data type, only that you cannot change the value. You can read the values from files into any data type. So you can have signals, you can have variables that connect to a particular file. For example, if you are doing image processing or some kind of data analysis, for example, vibration analysis, then you can have your data in an FPGA, in a file, and then it can be read through an entity and through the ports on an entity's evaluated, and then you get your results back that can also be written to another file, but this is usually implemented in the simulation environment. Data types in VHDL. VHDL has a very hard requirement on data types, which also means that the operations and functions to manipulate data that you create or that is available within the library and within the different packages has to be referenced and be used accordingly. So if you are creating a new data type, then you need to create the kind of operations and the kind of functions that must be used on them. So for example, if you create a data type weekday, then before you can add an integer to that weekday, for example, if you want to iterate from Monday to Tuesday to Wednesday, that means you need to implement another function. You need to create an operator and define it that knows how to manipulate this new data type with another data type of type integer. So data types in VHDL have very, very hard requirements, and that means that we need to be very sure that we have all the operators, or another way is that we extend existing data types such that they can easily inherit the available functions and operators. There are two main categories of data types in VHDL. We have scalars and we have composites. Scalars usually take single value. They can be of any data. They can be of any data type that are already available. So you can have enumerations of weekdays. You can have enumerations of logic levels. You can have integers. You can have floats, and you can have physical. And composites are usually aggregation of scalar data types. So when you aggregate them, you can have a record or you can have an array. Scalar data type, for example, enumeration, it's a list of values that are bound, and then when you create a data type of this, you statically give it the range of values or the range of possible assignment that it can have, and then in the implementation, the most efficient number of bits to represent these data values will be implemented. So this is usually convenient for the engineer, but in hardware, it's just a range of bits or bit vectors. So you also have integers, which can take values from positive, that are positive or negative. They are predefined in VHDL, and they usually have 32 bits, and they have a range from -2 to the power of 31 to +2 to the power of 1 minus 1. This also means that the implementation can take a lot of resources. So to avoid that, when you have when you know the limits or the range of the particular integer that you like to use, then it's possible to actually range it or to limit the possible values of this particular variable or signal that you're creating, even though it's an integer. By doing this range, it means that the most optimal or the most efficient or the least number of bits to represent this integer will be used. Otherwise, 32 bits will be used, and that can lead to long delays in your implementation. Floating points are available, and they can be of type scalar, and that also means they are also available in VHDL. They are also implemented as 32 bits, but they they are not supported directly for implementation, so you need to implement your own algorithm, or you need to buy a new component from a vendor that can help you to implement floating point. However, for simulation purposes, you can always use floating points as a data type. You also have type physical, for example, for time, for frequency, for voltage, for current. This also has no meaning in VHDL. It's only convenient for you as an engineer to know these things, how to know what kind of data type it represents, physical unit that it represents, and what kind of operation that you can use on them. Here are some examples of enumerated data types. We have Boolean, which is an enumeration of false and true. We have bit, which is an enumeration of 0 and 1. And they are predefined in the package 1076, which is part of the IEEE library. There's another package 1164, which is also part of the IEEE library, that defines standard logic and standard unsigned logic. These have many functions and many operators also implemented in these packages, and then it might be nice to be familiar with them so that one can know the kind of resources or competence or possibilities that are available in VHDL. So here is how we can implement standard logic or standard U logic. And here is the enumeration that is available within this type. We have uninitialized, when you create a signal and you don't give a value to it, and forcing unknown. So when you have an initialized signal and you are trying to add or perform some operations on it, then you can't get a result that is unknown, but then you can force it to a logic level 1 or a logic level 0, or you can drive it to a high impedance so that other components can easily bring it to a higher level or a lower logic level, or you can drive it to unknown that is weak so that it can be easily be driven. So weak, unknown, weak 0 and weak 1, these are for energy optimization and perhaps for short component to component communication, and they are usually used also in memories and I2C data types. We also have don't care. So when you have a signal that you give a value of don't care to a particular bit, then it means that whatever you drive to it, when it's combined to another signal, the other signal usually take precedence over it, because you have a value that you don't care what kind of operation it is. So standard logic is an example and is an extension or a resolved value of standard U logic. So standard U logic is unsigned, whereas standard logic can have both negative and positive values. So these are available in standards as a package, as listed here, and then they are available in the library IEEE. Composite data types are aggregation of scalar data types. So for example, if you already have your bit, then you can now have bit vector. Here we have two examples, one is signal and another one a variable, that are bit vectors that are 8 bits, and the definition is like they are going as 7 down to 0. And what this means is that the most significant bit is 7 and it's on the left side, and the least significant bit is position 0 on the right hand side. So composite data types can be more than just a vector. It can also be an array or like a matrix. So when you have an array of a vector, then invariably you have a matrix, for as given in this example here. So when you have a data type table 6 by 2, it's an array that has locations and columns that go from 0 up to 5, and at each column there are 2 rows. They go from 1 down to 0. So each bit location is of type bit, and it can be of type boolean, it can be of type logic or unsigned logic, but right now it's of type bit. And here is another example of how we can create a constant of type myTable, which I've recently defined, and then we assign values to it. Because this is a constant, it needs to have its value now, and this is how the values are organized in this myTable, that is an implementation of myTable 6.2. Another example of bit vector for binary or for octa or for hexadecimal is given below. So for example, when you have x, it can be any bit vector, it can be any signal or variable, and then here is how you can assign to it x83, which also can be written as b bit vector 1010 underscore and then 0011, or if you are defining it as an octal 8-bit or 6-bit, then each segment is from 0 to 7, and then you can organize it like this, being an octal. Attributes in VHDL have a convenient way to understand and to manipulate signals, variables, and other data types that we have in VHDL. So here is an example of a bit count, which is an integer that ranges from -3 to +5. And there are 2 things that we can note here, that the range and the direction are 2 different things. So the range is from -3 and to 5. So which means that the lowest number that can be in this bit count, which is an integer, is -3, and the highest possible value bit count can have is +5. However, the direction does not necessarily have to be from -3 to +5, but in this case, it is -3 to +5. The impact here is that -3 is on the least side because of the direction, and minus is on the left side because of the direction, because we always move from left to right, and -3 is the lowest side, so it's also on the left side. It's the lowest value and it's also on the left side. +5 is the highest value that bit count can have, so it's on the right hand side, and because of our direction left to right, +5 in this case is also on the right hand side. Here is another example of attributes, and we have a third example of how to use attributes. In this example byte, we create a new data type called byte. It's an array that has 8 bits. The most significant bit is 7, and we go down to 0. So 7 is on the left hand side, and then which means that the most significant bit is on the left hand side. Down to 0, the least significant bit is on the right hand side, and this is an example, an array of standard logic. So now we have 7 on the left side, even though it's the highest bit position, and we have 0 on the right hand side, even though it's the least bit position. And then you have so we can see that this is different from the organization in the previous slide. Now we have 7 on the left and it's the highest, and now we have 0 on the right and it's the lowest bit position. What this also means, one good way of using attributes is that we can have an example 3 like this, in which we create a for loop that has an iterator that iterates between the highest bit location of data type byte to the lowest bit location of data type byte. In this case, we know the bit location, the most significant bit location to be 7 and the least significant to be 0. But what if somebody else defines, or we inherited this byte from another module or package? What this means is that we can, using attributes, iterate over the entire bit location from the highest point to the lowest, least significant bit location, even though we don't know the range. We don't know if it is 7 down to 0 or 15 down to 0 or 10 down to 0. Okay, so now we can have a variable v underscore byte that at every location in the byte range, we assign 1 to it. Okay, so that's the essence of this for loop. Assign 1 to every location, starting from the highest bit location to the lowest. Operators in VHDL are very, very nice to have, because it makes it easy for us to be able to manipulate and to implement complex algorithms. So what this also means is that we should be familiar with the kind of operators that are available and which operators can be implemented or cannot be implemented. So we have operators, logical operators and arithmetic operators. All the logical operators are supported for synthesization, for synthesis, whereas only a restricted number of arithmetic operators are supported for direct synthesis. And we need to be familiar with which synthesis tool, or if we need to buy another module or algorithm or component that can help us to do a particular function or operation. For example, division is not directly supported, but then you can write your own division algorithm. Multiplication can be implemented in many ways, and most of the synthesis tool or hardware, FPGA fabric, already have a multiplier, perhaps integrated as part of a DSP module. We have you can implement exponentiation function and square root function or some other things, but these are usually something that you like to implement by yourself because of the complicated algorithm and different energy and area optimization that is possible when one has an optimal implementation. With this, we come to the end of this brief discussion on the basic issues with VHDL. Books, online resources, IEEE library and packages can be found from the common web search engines. So feel free to search for them simply by typing objects, classes, data types, operators, VHDL, and then you get a very good list of these kind of things. And then feel free also to check the links and to get familiar with the modules other people have implemented, how they combine operators, how they combine data types, how they use functions, how go into the libraries that are available. They are shipped usually with the most synthesis tool, see which functions are available, find a way how you can include them in your entities and how you can use them. Thank you.